These notes are over centripetal force. And so if we remember back to Newton's second law, so Newton's second law tells us the relationship between forces, mass, and acceleration. And so we have this equation, force equals mass times acceleration. Okay, and so we can utilize that basic formula and input our centripetal acceleration to find our centripetal force. Okay, and so if we plug in the equation that we found last time for the centripetal acceleration, so v squared divided by the radius, okay, we can find that the centripetal force is equal to mass times our speed squared or velocity squared divided by the radius. Okay, so just remember that it's very similar to the equation that we had for the centripetal acceleration, except that we're adding in mass because we're talking about force in this case. Okay, so centrifugal force is a fictitious force. And so I'm just going to skip to the example to kind of explain what that means. So if you are in a car, if you're a passenger in a car and the person driving the car quickly turns to the right, okay, you're going to feel like you are flying to the left. Okay, so it feels like you're going to the outside of the car. And it feels like there's a force that's basically pulling you to the opposite direction. Okay, or like in this example, if the car turns left very sharply, you feel like you're being pulled to the right. Okay, and so that's not what is actually happening there. Okay, so what's really happening is that your inertia is just continuing to take you in the forward direction. Okay, but since the car is turning, it makes it feel like, even though you're still going on this path, it makes it feel like you are getting pulled to the outside of the car, to the right of the direction of the turn. Okay, and so this is known as a non-inertial frame of reference. So you, as the observer inside the car, feel like you are being pulled to the right, but it is not what is actually happening. Okay, if we had an observer who was standing on the sidewalk looking at you, okay, what they would see is that you are being pulled or pushed by the car to the left. Okay, so that would be the inertial frame of reference. Okay, so the key thing just to note is that we have these forces that are perceived by different reference points, and some of them are fictitious because what's really happening is that you're continuing on your same path, but it feels like you're being pulled in the opposite direction of the direction of the car. So we're going to be talking about different applications of centripetal force. And so today I'm just going to go over two of them, and then we'll go over the next three in the following meeting. So pilots and astronauts undergo high G training to prepare themselves for flights involving extreme acceleration. So at high accelerations, our blood actually moves from our head to our feet, which can result in a loss of color vision called grayout, tunnel vision, and blackout. So obviously these are very dangerous things to occur, or situations to occur, to people such as pilots and astronauts that have these large flying equipment that they have to control. Okay, so in particular, pilots and astronauts practice techniques that prevent G-lock. Okay, and so G-lock is just G-force induced loss of consciousness. So it could be deadly, as a pilot would lose control of the aircraft. So high G training takes place in a human centrifuge. So here we have an image of a human centrifuge. And so basically they sit in this little pod, and then the arm rotates around faster and faster, causing different centripetal forces or G forces. So without training, most humans can tolerate 4 to 6 Gs. But with training and a specialized suit, it can be improved up to 9 Gs. So it's quite a difference there that they can experience utilizing the training and technology such as a specialized suit. Okay, so for example 1, how many G's would a pilot in a 14-meter long centrifuge experience? So 14 meters, that would be our radius, right? And then we're given each of the different situations. So first they give us the speed of the centrifuge. If the speed was 16 meters per second, what would be the force felt in G's? Or no, what would be the centripetal acceleration in G's? And then for part B, the rotational period is 3.3 seconds. So what is the centripetal acceleration? And then the frequency of rotation is 0.5 hertz. So they give us frequency. They want to know what the centripetal acceleration is. Okay, so we're treating each of these as different problems. And we're going to be utilizing the 3 different equations that we derived in the last section. Okay, so for the first one, we have that the velocity is 16 meters per second, okay, and then our radius is going to be 14 meters, and then they want to know what is our centripetal acceleration, okay, so we'll use that first equation, the AC equals V squared divided by R. Okay, so when I plug in my information, I'd get 16 squared divided by 14. And we find that our AC is equal to 18.286 meters per second squared. Okay, and so that is a correct answer, but it does ask how many G's. Okay, and it's important to note that 1 G is equal to 9.8 meters per second squared, which is our gravity here on Earth. Okay, so in order to convert this to G's, we need to divide this number by 9.8 meters per second squared, and we'll get that our centripetal acceleration in G's is 1.87 G's. Okay, for part B, they give us the period, and so we're going to be using the second derived equation that we found in the last section. So AC equals 4 pi squared R divided by the period squared. And so plugging in the information, AC equals 4 pi squared. Our radius was 14 divided by our period, which is 3.3. We square that, and we'll find that our AC is 50.75 meters per second squared. Once again, we do want to get it in G's, so we're going to divide it by 9.8 meters per second squared and get that our AC is 5.18 G's. Right, and then for the last section, part C, they give us frequency. So we're going to use the last derived equation that we found in the last part. And so AC equals 4 pi squared RF squared. All right, so plugging in our information. Our radius was 14. The frequency they gave us was 0.5 hertz squared. Okay, and we find that our AC is 138.17 meters per second squared. Once again, we need to calculate it in terms of G's, and we'll get that our AC is 14.1 G's. For this last part, artificial gravity, we can utilize centripetal acceleration to help astronauts out in space. So due to being in constant free fall around Earth, astronauts working in the International Space Station suffer from nausea, loss of bone mass, and loss of muscle mass, and reduction in blood volume. Okay, so as humans and our bodies are made to experience gravity or experience the force of gravity. Okay, so up in space where you're in constant free fall, you don't have that normal force working on you, it can mess up our bodies and cause lasting effects. So to counterattack these physiological effects, a rotating torus, a donut-shaped space station, has been suggested for long space missions. So here we see the torus of the space station. So a rotating torus would provide a centripetal force towards the center. So very similar to the pull of gravity that we feel towards the center of Earth. So if the torus is rotated fast enough, the astronauts can feel a normal force equal to their normal weight on Earth. So for this problem, a torus-shaped space station has an outer radius of 9.3 meters. Determine the speed, period, and frequency of rotation that allows the astronauts to feel half their normal weight on Earth. So half is the key term here. But the three things we're going to be calculating are speed, period, and frequency. Okay, so first off, let's just kind of draw a free body diagram. So if I have my torus shape, okay, and then I have a radius of 9.3 meters. Okay, a person standing here in normal would feel the force of gravity, and then we would have the normal force, right? So on Earth normally, our Fn equals our F of g, right? Because if the object is not accelerating, it's just sitting on a table, or you're just standing on the ground, the force of gravity pushing down on you is going to be equal to the normal force pushing back up. So if we wanted to make it so that the astronauts feel half their normal weight that they would on Earth, we would need to find that F of n would equal half the gravitational pull. So mass times the gravitational constant. Okay. So for this, our F of n and F of c are equal. Okay, because if F of n is pulling upwards towards the center of the circle, our centripetal force does the same thing. It's always going to be pulled towards the center as well. Okay, so F of n and F of c are going to be the same. So for finding speed, we're going to use the equation, our centripetal force is equal to 1/2 mass times gravity. Okay, so I just plugged in F of c because F of n and F of c are the same. I plugged in F of c into this equation to find this equation. Okay, so remember that we know that F of c is equal to the mass times velocity squared divided by the radius. Okay, so I can use this equation and plug it into my F of c. So I'm going to go ahead and do that. So mv squared divided by r equals 1/2 m times gravity. Okay, what ends up happening is that my masses actually cancel. And if I simplify this equation to solve for v, I get that v equals the square root of gr divided by 2. Okay, and so you will have a very similar problem in your guys' homework. And so this equation can be used to find the force felt if we want to half the normal weight. So if it wasn't half, it would be a different equation, but in your guys' practice problems, it does ask for half their normal weight. So you can just use this equation for that. Okay, so now I can plug in the information that I have. So V equals the square root. The gravitational pull on Earth is 9.8 times our radius, which is 9.3, divided by 2, and then we'll find that V equals 6.75 meters per second. So that's our speed, our instantaneous speed. Okay, for period, once again, we can use the Fc equals 1/2 mass times gravity. Okay, and looking at this equation here, okay, we know that F of c equals mass times the centripetal acceleration. Okay, and then so for this problem here, what I did was I just plugged in the v squared divided by r for AC. I can also plug in the equation that we have that includes period, which is the 4 pi squared r divided by period squared, into this to find FC, or for f of c. Okay, so I'm going to do that here. So f of c is going to be equal to m, and then 4 pi squared r divided by period squared, and that equals my 1/2 mass times gravity. Okay, once again, mass is going to cancel out, and then when I rearrange this problem to solve for t, I get that t equals the square root of 8 pi squared r divided by g. Okay, where g is the gravitational constant here on Earth, and then r is our radius. So plugging in our information, the radius is 9.3 divided by 9.3. I get that my period was 8.66 seconds. Okay, so that's the time it takes to make one rotation. Okay, and then frequency is pretty simple. So if you remember, frequency is equal to, frequency is equal to the inverse of our period. Okay, so what I can do is plug in what I got for my period in the last part. So F equals 1 over 8.66. And so whenever I divide that out, I'll get that my frequency equals 0.116 hertz. Okay, so if you don't really understand how I derived each of these equations, it's not that big of a deal. You'll just utilize these two equations for your homework. So this equation and this equation, and then this equation for your homework. But note that these equations are only good for if you are trying to find half the normal weight of a person on Earth.